Hey guys, so in this video I'm going to discuss continuous distribution functions, some properties of continuous distribution functions. In the previous video I discussed example 5.20 and example 5.19, and in this video I'm going to discuss CDF, and along with that I'm going to discuss example 5.22. So let's just start. So continuous distribution function. I'm going to write some properties of distribution functions. Wait. Definition. If x is a continuous random variable with the PDF or probability density function fx with the PDF fx, then the function is called the distribution function, or also known as cumulative distribution function. Continuous distribution function. If x is a continuous RV random variable with the PDF fx, then the function fx is equal to probability x less than equal to x is integrating this PDF over the limits minus infinity to x is called the distribution function, also known as cumulative distribution function, right? So what this means is this integral from negative infinity to x ft dt, right? What this means is we are calculating the area under the curve from the lower limit, that is negative infinity in this case, till any point x, till any point small x, right? So this is known as the CDF of CDF fx, right? Where x, this small x is the point, wait, is the point, and this capital X is the random variable. X is the random variable. That can take different values, and this small x is the specific point. This small x is the point. Capital X is the random variable, and this small x is the point. So the small x can take any value between negative infinity to positive infinity. Why? Because I've written here in the first slide that my small x, this is my small x lies between minus infinity and infinity. Let's discuss the properties now. So a cumulative distribution function will always lie between 0 and 1 because it's the area under the curve, right? This, let me just write this as the first property. The second property will be f dash x, the first derivative of the CDF is equal to the PDF, which is greater than equal to 0. And because my f dash x, which is my f of x, my f dash x, which is my f of x, is greater than equal to 0, implies that my fx is a non-decreasing function of x. I'm seeing the properties from the book and then I'm writing them so that I don't miss any point, right? So f dash x is equal to fx greater than equal to 0. Fx is a non-decreasing function of x. Right. I can also explain this property to you guys. Wait, let me just write this again. Right. So f dash x is greater than equal to 0, right? So what this implies is that if my x1 is greater than my x2, then my f of x1 is greater than my f of x2, right? And we can see that from here. For example, my lower limit is negative infinity and my x1 is greater than my x2, right? My x1 is greater than my x2. So my x2 will be somewhere here. For example, let us suppose that my x2 is here and my x1 is here, right? So my CDF says that find the limit from negative infinity to the point x ft dt, right? So this is my CDF. When my x1 is greater than my x2, this implies that my area under the curve from negative infinity to x1 is greater than my area under the curve from negative infinity to x2, right? So you can see this area is less than this whole area, see, including this also, right? So automatically we know that f of x1, which is the area under the curve from negative infinity to x1, is greater than the area under the curve from negative infinity to x2, right? I'm just removing this now because I have already written this here. This fx, just the CDF is just the area under the curve from negative infinity to any point x, and the area under the curve from the lower limit to any point x, where I'm integrating over the PDF, right? Because my PDF is the function, this is the probability function, so I'll be integrating that only. Now my next property says that third property says that f of negative infinity is equal to limit x goes to negative infinity. Now x goes to negative infinity f of x, which means that limit x goes to negative infinity x. This is the formula of my CDF ft dt, and this will imply that if I just put in the limit, if I just substitute negative infinity, so this will give me negative infinity to negative infinity ft dt, which is 0. Therefore my f of negative infinity is equal to the limit x goes to negative infinity fx, which is equal to 0. my fourth property says that f of positive infinity is equal to limit x goes to positive infinity fx one. So this means that my f of infinity is equal to my limit x goes to infinity fx, right? So when I just substituted infinity in place of x, I got the integral over negative infinity to positive infinity, which is equal to the area under the whole curve, the area under the total area under the curve, right? So from negative infinity to positive infinity, this implies the area, the whole area under the curve, right? So this implies the whole area under the curve, from negative infinity to positive infinity. Now let's just take one example and try to prove all of these properties. Let my fx be kx square, where my x lies between 0 and 1. So let's just find the value of k first. For finding the value of k, I just need to integrate this over the limits of x. So this gives me 0 to 1 kx square dx, and this should be equal to 1. This implies that my k x cube upon 3 is equal to 1, which gives me k by 3 is equal to 1, which implies that my k is equal to 3. Moving on, when my k is equal to 3, this gives me my fx as 3x square, where my x lies between 0 and 1. Right. My x lies between 0 and 1. Now let's just check the property. So my f of negative infinity should be equal to 0. Now why is this happening? Because my fx, which is my PDF, is only defined over the limits 0 and 1, right? So I can write this PDF, this 3x square, where my domain is 0 to 1, I can write this as 0. Elsewhere 0, I can write this as 3x square when my domain of x is 0 to 1, and I can write 0 elsewhere, right? 0 elsewhere. Now elsewhere means that on any real value of x other than 0 and 1, this PDF is 0. Now my CDF will be, if my PDF is 3x square, my CDF will be, I just need to integrate this, right? So integrating this 3x square dx over 0, because 0 is my lower limit, to any value, any point x. So let me just write this as 3t square, right? This will be easier then. We just write t inside, and we write x in the limits, so that it becomes easier to represent, and we don't get confused or we don't make any mistake while putting in the limits, right? This is the only reason why we write 3t square dt inside the integral, and outside in the limits we write 0 to x. So this is just the lower limit till any point x, right? So this is 0 if my lower limit is 0. So we are finding the CDF over any x lying between 0 and 1, right? It can be 1 also, but yeah, I'm just writing this as 0 to x. So this will give me 3x cube 3t. This will give me 3t cube upon 3 over 0 to x, which will give me ultimately 3 and 3 will go away, x cube minus 0, so this will give me x cube over 0 over my x lying between 0 and 1, and this will be 0 elsewhere, right? 0 elsewhere, because we don't have any PDF over the limits. So let me just write my CDF again. So we just found the integral, and we found that my CDF is equal to x cube when my x lies between 0 and 1, and this is now I made a mistake here. This is not 0. See, I'll be explaining you. This is a very important concept that I'm going to explain you guys. Now, for the limits where my x lies between 0 and 1, for my x lying between 0 and 1, we had a PDF that I integrated over the lower limit 0 till the upper limit any point where my upper limit was any point x which was lying between 0 and 1. This gave me my CDF for any x lying between 0 and 1. But what if my x is greater than 1? But what if my x is greater than 1? See, but what if my x is greater than 1? So for my x being greater than 1, let me draw the diagram or the bell curve, right? So now we know that this whole area of any x lying between 0 and 1, this is equal to x cube, right? And for example, I extend this line, right, and I write this, for example, this is 2, let my x be 2, right? So I don't have any area before this, I don't have any PDF, right? My PDF is ending over here, over 1, right? So 1 is my upper limit. This means that I don't have any function here. I'm just trying to force you to imagine this. This is not a clear diagram, this is not used in any book, but I am just trying to make you imagine this intuitively. So there is no PDF over here, right? There is no function over here. Nothing is here. Nothing is present over here, right? But we already have this whole curve, right? We have this whole area till 1, right? So my CDF for any value x greater than 1, let me just write this as let me just include 0 and 1. It is not important, it doesn't make any difference, even if I include 1 over here or here, it doesn't make any difference because it's a continuous distribution, but I just include this, right? So what will my CDF be over here? This will be from 0 to 1 fx ft, I am just writing t inside, so this will be from 0 to 1 ft dt from 0 to 1, and I don't have any function over here. So can I write 0 here? Let me just write 0 here because I don't have any function over here. There is no probability present. But before this point 2, I had point 1, and from 0 to 1, I had probability 1. So this was 1, right? The whole area under the curve from 0 to 1, from a lower limit to my upper limit, gives me 1. Gives me the probability 1. So this means that my PDF was now my PDF for from 0 to 1, this function is 3x square, right? So I just need to integrate this over 0 to 1. So this gives me 0 to 1 3x square dx, which is equal to 3x cube by 3 from 0 to 1, which is 3 and 3 goes away. This gives me 1. Therefore my fx is my CDF finally becomes x cube when my x lies between 0 and 1. Now again, doesn't matter if I include 0 or 1, and becomes 1 plus 0, so 1 for any x greater than 1, right? Because I have the whole area under the curve and for example my x is 2 here, but I don't have any function present over here, right? My function is, my PDF is ending. I only have my PDF over the limits 0 to 1, so I don't have any function. So this area is 0 because I don't have any curve, and this area under this whole curve is equal to 1 because the probability over the lower limit and the upper limit is always equal to 1, the total area under the curve, right? So this is my CDF. Now what if my x goes to negative infinity, right? If my x goes to negative infinity, this will be 0 because I don't have any PDF, I don't have any CDF over x being less than 0, right? For example, let's just see this. So for example, let me just draw this here. So this is 0, this is 1, and for example this is 2. So this means that this is my area. I only have a PDF defined over the limit 0 and 1, right? So so for any x, or this is, let me just write this as 2, and this is going to infinity. Where is my cursor, right? Let this go to positive infinity, right? So this is positive infinity extending to positive infinity, and going to negative infinity, right? So for any x greater than 1, I'll be always having 0 here because I don't have any PDF, and this area being included. For any x greater than 1, I'll be having the area from 0 to 1, and then from 1 to x, but there is no PDF over 1 to x, so this will be 0. So this will always be, and this will, from 0 to 1, this will always be equal to 1. So so my CDF for any x going towards infinity will always be equal to 1. Now from negative infinity, if my x approaches to negative infinity, I don't have any function present over here, right? And the first function that I encounter will always be when I go for any x greater than 0. So I don't have any PDF. I don't have any PDF before the lower limit 0. I don't have any function over the I don't have any function present for any value of x that is smaller than 0, right? For greater than 1, I already have a PDF present over 0 to 1, so I'll be including that. And for 1 to x, I don't have any PDF, so that will be 0, right? So for any x approaching to negative infinity, this will be 0 because I don't have any function. And if I write any x going to negative infinity, fx dx, not fx dx, this is fx only. So my fx is 0 for any x line going to negative infinity. So this will be limit x goes to negative infinity 0, which is equal to 0. This means that my f of negative infinity is equal to my limit. Let me just write this on the next page. This means that my f of negative infinity is equal to limit x goes to negative infinity fx equal to 0. Right. Now let's just check the other value when my f is going to positive infinity, right? So now I don't have any PDF for x going to positive infinity, but I have a PDF for x going from 0 to 1, and the total area under the curve from 0 to 1 will be 1, right? So I'll be writing my CDF now from 0 to 1 plus 0 because I don't have any PDF present which I can integrate over from 1 to x, right? So that is 0, that area is 0 because there is no curve. So, and this will always be equal to 1 from 0 to 1. From 0 to 1, this will always be equal to 1. This is always equal to 1, fx dx. So this is always equal to 1 plus 0, which is equal to 1. So my f of positive infinity is equal to 1. Similarly, limit x going to positive infinity fx, and this will be equal to, this will again be equal to 1, right? When my fx my x is going to positive infinity fx, so I can write this as limit x going to positive infinity negative infinity to x, and this is fx dx. Now I can just substitute positive infinity here, negative infinity to positive infinity fx dx. Now I can break this negative infinity to positive infinity from this will be from negative infinity to 0. Again, I don't have any any PDF over here, I don't have any fx present over here, so this will automatically be 0. And from 0 to 1 I have a PDF fx dx which was 3x square, so this will be equal to 1, so this is equal to 1, the total area under the curve. And again, from 1 to x I don't have any PDF, I don't have any fx dx defined for x greater than 1 to x, and I don't have any PDF defined for negative infinity to 0, so this will again be 0, so this will also be equal to 1, right? So we proved both of those properties using an example wherein my f of negative infinity is equal to my limit x goes to negative infinity fx, which is equal to 0, and my f of positive infinity is equal to my limit x goes to positive infinity fx, which is equal to 1. We proved both of these properties. Now what's the next property? Fx is a continuous function of x on the right? So for example, let's just check the continuity of x at 1. Let's just check if this function fx that we took where my fx is my f capital X is, now we can write this as 0 for any x less than 0. We'll be writing when my x lies between 0 and 1, I can write this as 3x square, and for my x greater than 1 this will be equal to 1, right? So let's just check the right continuity at wait, this is the, I wrote the PDF, wait, this is the 3x square was the PDF, not the CDF. X cube is my CDF, right? Let me just check if I wrote this incorrectly somewhere or the other. Yeah, right, so we wrote this x cube, x cube. So let's just check the right continuity at point 1. So let me just go to the next slide. Yeah, so at x equals to 1, f of 1 is equal to x cube, so 1, the cube of 1 is equal to 1, and when my limit x is approaching to 1 of x cube, so this will also be equal to 1 cube, which is equal to 1, so my f of 1 is equal to my limit x goes to 1 positive. Wait, we are checking the right continuity, right? I checked the left continuity in this case, so limit x goes to 1 plus fx, and whenever my x is greater than 1, my fx becomes 1 for any x greater than 1. For any x, 1 plus indicates I am approaching the point 1 from the right side, so I have any number greater than 1, slightly greater than 1, I am approaching it from the right side of the real line, right? So this means that my CDF or my function, here I am just treating CDF as a function, so my function for x greater than 1 is equal to 1, so limit x approaching 1 from the right side, 1 plus, and my fx is 1, so this will be equal to 1, hence my function, hence f of 1 is equal to limit x goes to 1 positive f of x implies right continuous at point 1, at point x is equal to 1. Now let's just check the right continuity at x is equal to 0. At x is equal to 0, f of 0 is 0 cube, which is equal to 0. And if I check the right continuity, now for checking the right continuity, limit x 0 plus, now my fx for when I am approaching x from the right, when I am approaching 0 from the right hand side, so my function will be, my x is now slightly greater than 0, so whenever my x is slightly greater than 0, my function will be x cube, right, for any x lying between 0 and 1. So this will be x cube. So this is 0 cube again, and this is 0. So my f of 0 is equal to my limit x goes to 0 positive x cube. Shit, I don't know what happened, which is equal to 0, right? So write continuity at x equals to 0, right? So we proved this property also, that fx is a continuous function, that CDF. Just write this property. Let's just write this property formally now. Let me just check the property number. Yeah, so this is the fifth property. So the fifth property says that the CDF, my cumulative distribution function, is a continuous function, sorry for my handwriting, is a continuous function of x on the right. Continuous function of x on the right. Now let's just discuss example 5.22. So example 5.22 is a bit different from what we have discussed so far, right? So let's just try and solve this. If x and y, example 5.22 says that if x and y are independent random variables, RVs, with the distribution function fx and fy respectively, obtain the distribution functions of a u is equal to max of x comma y and b part v is equal to min of x comma y. So we need to find the CDF, or the distribution function. CDF is the cumulative distribution functions, or we can also say them as the distribution functions only. So we need to obtain the distribution functions of u and v. So we need to find f of u, small u, this is capital U. We need to find this, and we need to find this and this. So let's just start from the part A. Now it is given to us that x and y are independent random variables. So for independent random variables, we can say that the property of independent random variables says that the probability of x intersection y is equal to probability x into probability y. Just remember this will come in handy. Yeah, so for part A, u is equal to max of x comma y. So this says that now f of u, small u, we know from the definition of CDF that f of u, and this is small u, is equal to probability capital U less than equal to small u, where small u is the point and capital U is the random variable. This is equal to, now my u is given to me as max of x comma y. So I can just substitute it. So max of x comma y less than equal to u. This says that the maximum of x comma y should be less than equal to u. So for example, if my x is greater than y, my x is also less than u, and if my x is greater than y and my x is less than u, this automatically implies that my y is also less than u. X is equal to 2, y is equal to 1. So if my x is less than 2, if my x is equal to 2 and my y is equal to 1, right? So if my x is equal to 2 and my y is equal to 1 and my x is less than u, this automatically implies that my y, which is already less than x, so I'll just write x is greater than y. Yeah, so if my x is greater than y and my x is less than u, this automatically implies that my y is less than u. So what I can write this as, I can write my CDF for u as probability max of x comma y less than equal to small u, which implies that probability x less than u intersection y less than u. This means that now I can apply the property of independent random variables, and I can separate this out, x less than u and probability y less than equal to u, right? And px less than u means we have the CDF of x where my point inside is u, and this term is my CDF of y when my point inside is u, right? This implies that my f u is equal to drawing a box around all of this. Now let's just solve the part B. Now part B says that v is equal to min of x comma y. Now this is tricky. Why? I'll be showing you. Now f of v, where v inside is a point and this v is a random variable and this is a point, this is equal to probability capital V less than equal to small v, which is a point, and my capital V is given to me as min of x comma y. So this is min of x comma y less than equal to small v. This implies that now I cannot straight away write this min x comma y less than equal to v as x less than equal to y and y less than equal to v, right? And why so? I'll be showing you. Now we have written min of x comma y. What if my x is less than y, right? If my x is less than y, I can write this as x less than equal to v, right? If my x is less than y, I can write this as min of x comma y less than equal to v. So if I write this as, let me just write this again. So min of x comma y less than equal to v, if I write this as x less than equal to v intersection y less than equal to v, right? Now this is the first statement and this is the second statement. I'll be explaining both of those statements. Which of these two statements do you think makes more sense? If the minimum of x comma y is less than equal to v, can we say that x is less than equal to v and y is less than equal to v? We don't know if x is less than v or y is less than v, right? So for example, if y is less than if y is the minimum from x comma y, if y is the minimum from x comma y and y is less than equal to v, we cannot imply that x is also less than equal to v. What if x is greater than v, right? But in the second statement, the first statement, let me just show you guys. Let me just take an example and show you guys. For example, here so let my x be 2 and my y be 1. So min of 2 comma 1 is 1. So we are saying that min of 2 comma 1 is less than equal to v, which implies that 2 is also less than equal to v, intersection 1 is also less than equal to v. But this is wrong. Why? Because min of 2 comma 1 is min of 2 comma 1 being less than equal to v means that 1 is less than equal to v. But through this statement, can we say that 2 is also less than equal to v? We cannot, because v can be 1.5 also. V can be anything. V can be anything, right? But saying that from the minimum of two numbers, can we imply that minimum of two numbers being less than v, can we imply that the greater of the two numbers will also be less than v? No, we cannot say that. We cannot say that. But in the second statement, what I did was I just wrote this min of because this was probability, so I just wrote this min of x comma y less than equal to v as 1 minus probability min of x comma y greater than or equal to v. Both of these things mean the same thing. I just subtracted it from 1, right, because it's a probability curve. Now this statement, what this statement means that if my this statement says that if my x is equal to 2 again and y is 1, so 2 comma 1 is greater than or equal to v. So my minimum of 2 comma 1 is 1, minimum of 2 and 1 is 1, so 1 is greater than or equal to v. Now we can say that if 1 is greater than or equal to v, we can imply that 1 is greater than v, intersection 2 is greater than v. This statement makes sense. But the previous statement was saying that because the minimum of 2 comma 1 which is equal to 1, the previous statement was saying that because of the minimum of 2 comma 1 which is 1 is less than equal to v, we can also imply that 2 which is the maximum will also be less than equal to v. But this is not true. This cannot happen. What if v is 3? What if v is 3? Then this will be possible. But what if v is 1.5? Then this statement would be false. Then this statement would be false. And even if we have one value, by trial and error, even if we have one value to prove that this statement is not being true for all values, then we can say that this statement is false, right? But in this statement, the minimum of 2 comma 1 is greater than equal to v. This implies directly that the maximum will also be greater than equal to v. But if my minimum of 2 comma 1 is less than equal to v, we cannot say that the maximum will also be less than equal to v, right? So now let's just come to the question. So we were finding fv small v, which is equal to, I hope you guys get the point. If you have any doubts, just write it in the comments, and I'll be uploading one more video with taking the same example and taking some more examples on min and max, and I'll be explaining this concept again to you guys. But just this is hard to understand in the first go. It was really hard for me also. So if you just remind the video or just let me know in the comments, I'll be uploading one more video explaining you guys this concept, right? But I hope you guys get the point. So f of e min of x comma y less than equal to v. So we cannot generalize the statement, but we can generalize 1 minus p. So 1 p min x comma y is equal to less than equal to v is p 1 minus p min x comma y greater than equal to v. And now we can generalize the statement. This means that x is greater than equal to v, intersection y is greater than equal to v, which says that now these are independent RVs, x and y, so we can just separate them out. So this means, so this gives me and p y greater than equal to v. Now I can write this term as and this term as 1 minus p x less than equal to v, and this term as 1 minus p y less than equal to v, which means 1 minus f x, again the CDF of x when my point is v, into my CDF of y when my point is v. So my CDF for v will be 1 minus, wait, I made a mistake here, I'm so sorry. This will be, this will not be this, let me just write this again. This is 1 minus fx over v, right? So this term alone is equal to fxv, and this term alone is equal to fyv. So ultimately what this will become is 1 minus the initial one minus 1 minus fxv and 1 minus f of yv, right? 1 minus, let me just use my eraser. So this gives me 1 minus fxv, 1 minus fyv. Now let's just obtain the PDF from our CDF, and we know for obtaining my PDF from my CDF we just need to differentiate the CDF, right? So we just need to differentiate this to obtain the PDF of u and v. For example, we are finding the PDF for u first, so we just need to differentiate u with respect to u only. This means that we need to find d by du of now my CDF in the first example was this. This is the product of the CDFs of x and y when my point is u. So this is fx u and fy small u is my point. So this gives me fx u into, just applying the product rule of differentiation, and plus fy u into f of x u. Can I draw a box here? Yes. And for part B, where my f of v small v, b is my, and this is my point, was equal to 1 minus fx u 1 minus f y u. I can just open the brackets, so this will give me as 1 minus 1 now minus fyu plus, so minus plus fyu, again minus fxu and positive, so positive fxu. Now this is positive and negative, so negative fxu fyu. So just differentiating this d of dv, d by dv of f v small v. This gives me 1 and goes away, this was already 0, and after differentiating also this will give me 0 only because it's a constant term. So this gives me 0 plus this will become fyu, this will become the PDF of x when the point is u, and this will give me, now applying the product rule, this will give me fxu fyu minus fyu fx if I take fxu common and fiu common, this will give me my fv small v as, this was the PDF of u, the PDF u. This will be now taking fxu common, so this will give me fxu 1 minus fyu plus fyu 1 minus fxu. Fx, wait, not u. Why am I writing u again? Sorry. I just wrote this by mistake because of my previous part. I just, I had the habit of writing u inside the bracket. This is small v, this is small v, right? So just change this to small v. This is small v, again, not u. This is small v, small v, v, small v, this small v, right? Because we are talking about v here, not u. So this gives me fxv 1 minus fyv. This is the CDF and this is the PDF of x, and plus the PDF of y with and the product 1 minus fxv, where fxv is the CDF of x, right? And small fyv is the PDF of y. So this is my PDF. Obtaining the PDF from the CDF. So first we found the CDF, then we found the PDF. So thank you guys for watching this video. It was quite dark when I was recording this video. That's why sometimes I don't think you would have been able to see me properly, because there isn't much lighting in my room. If I switch on my main light, my face becomes all white, and you won't be able to see me then. I hope you guys like the video. If you guys like the video, and if you have any doubts, just like and put in a comment. It encourages me to put in more videos. And if you have any kind of doubts, just let me know in the comments. I'll be uploading more videos on specific topics if you are having recurring doubts on those topics. Thank you so much. Please share the video and also subscribe. Thank you.